All right, in this lecture, we're going to talk about the metric-induced properties of the Riemann tensor. And that's just a fancy way of saying that we are going to study all of these related tensors, the Ricci tensor, the curvature scalar, the Weil tensor, which is the conformal tensor, which can be written in a bunch of different ways. I can just write it alpha, beta, gamma, delta is a common way of writing it. The Einstein tensor, alpha, beta. And then there's this one really interesting one, which I'm probably going to digress into today, and it is called the double dual. It'll look like this, the way Meissner, Thorne, and Wheeler likes to put it, alpha, beta, gamma, delta. And this is called the double dual. And that's that one's, to me, I'd like to get on that one quickly. These guys are actually pretty easy. Why is it called metric-induced properties? And the reason it's called metric-induced properties is because you need to get at them, you need to raise and lower indices. And in order to raise and lower indices, you have to have a metric, right? You have to have a metric in order to raise and lower indices. We've already kind of done this, right? Because we showed that alpha, beta, gamma, delta exists, and you can't. This is what we derived when we studied geodesic deviation and moving around a loop. We ended up with this guy. That's the real Riemann tensor, and then we get this guy, which is sort of a metric-induced variant, right? Because we just lowered that alpha. But what was important is in this metric-induced variant, we know that we had antisymmetry in the first two indices and antisymmetry in the second two indices. And that is what's going to give us this notion of the double dual. So I want to review this sort of antisymmetry business, which is really the notion of two forms. And I'm going to try to do sort of a lightning version of our two-form analysis from the what is a tensor series. I'm not going to do a total discussion of n forms, and I'm not going to do anything about their geometric interpretation. I'm just going to do sort of a lightning fast replay of what two forms are, and then we'll see how we can use two forms, which remember, two forms are members of the 0-2 tensor product space. They're antisymmetric members. So, and this guy here, as written, is a 0-4 form. But we're going to see how these two forms matter in this regard. So we're going to do this, in this lecture, we're going to do this review of two forms, come to understand this guy as a tensor product of two forms, and then we're going to try to understand what this guy is. Okay, let's begin. So we're going to begin with a tensor we're going to call, which we'll call F, and F is antisymmetric. Now I'm writing it out in the basis of the tensor product space 0, 2. So this is the covariant, well, the components are all completely covariant, right? These are all covariant components in the tensor product space. And the basis of the tensor product space is given by these guys, right? These are the basis vectors of the tensor product space. That is how we understand a tensor product space. So each of those is a basis vector. Now there's a couple basis vectors missing, right? We have E0 tensor product E0, that's not there. E1 tensor product E1 is not there. In fact, every one of the form E alpha tensor product E alpha is not there. And that's because we've already stipulated this is antisymmetric, so clearly these guys will all have to be 0 because their component F00 would have to equal, you have to have F00 equals minus F00, and that can only happen when F00 is 0. So we only have, so already we've lost 4 dimensions. Just by saying that F is antisymmetric, there are 4 dimensions that are gone. This guy has 16 dimensions, right? There's 16 dimensions, but 4 of them are missing. So now we're down to 12. But we actually drop all the way down to 6. And the reason we drop to 6 is because this guy here, well, we know that it's being antisymmetric. We know that that component, F01, has to be the opposite of F10. And we know that because F alpha beta equals its antisymmetric part, f alpha beta. That's the definition of an antisymmetric tensor when written in this basis. And we've already figured out that this guy here is equal to 1/2 f alpha beta minus f beta alpha, right? Which means that we have 2 f alpha beta equals f alpha beta minus f beta alpha, and then we just move this over here, we lose the 2, and we get f alpha beta equals minus f beta alpha. So we know that these coefficients are going to be opposite of each other. So we can enforce that in our description here, and I'll do that in red. I'm going to say this is actually minus 0, 1, right? And I replace this with 0, 2, and I put a minus sign there. And I replace this with 0, 3, and I put a minus sign there. I replace this with 1, 2 with a minus sign, with 1, 3 with a minus sign, and with 2, 3 and a minus sign. So once I've done that, I've now opened up the possibility of factoring out f01, combining this term and this term together, and factoring out f01. Wait, something's wrong here. This needs to be a 1, 0, right? Let me erase this. That needs to be f1, oops, f1, 0. Let me make sure I got all the rest of them correctly, right? That's 0, 2, this is 2, 0, 0, 3, 3, 0, 2, 1, 3, 1, 3, 2, 1, 2, 1, 3. Yeah, for some reason this one was backwards. Okay, so now I'm going to factor out the f01s, and what will I get when we do that? Well, let me move over to here. And this is what we get. I factor out the f01s, f02s, I've just factored out the common coefficients, and I combine the two basis vectors together. And now you see we're down to 6 basis vectors, right? Because this is a vector in the tensor product space, that is. So the difference between the two is, and if I just say, okay, this is our new basis vector, then I have 6 of them. And the only thing I've assumed in doing this is that f was antisymmetric. Once I made that decision, I always will be able to reduce a 0-2 antisymmetric tensor into this form, which means I'll always be able to have 1, 2, 3, 4, 5, 6 basis vectors, which means that I have now found myself, by just demanding antisymmetry, I've now found myself to be in a subset of a subspace of the 0-2 tensor product space, and that subspace is the second exterior power. And F is what we call a 2 form. And now, in order to make this a little easier, I'm going to rename all of these basis vectors and give it a simple single symbol to represent, let me erase this here, to represent each basis vector, and that symbol will be E0 wedge E1, E0 wedge E2, E0 wedge E3, and so forth. And now I will write down this antisymmetric tensor in this new basis in the following way. I'll write F alpha beta E alpha wedge E beta. That looks okay, except for the problem that, if you'll notice, we don't have all alpha betas here. We only have alpha is always smaller than beta, right? I have every combination of alpha beta as long as alpha is smaller than beta. So I have alpha smaller, less than beta. And that's important because if I didn't, I would be counting things twice. And so what I'm going to do is I'm going to throw little lines on this, and that little line is a shorthand way of enforcing alpha less than beta in the sum. It's still summed over alpha and still summed over beta, and it's still upper-lower sum, just like the Einstein convention, but I'm not summing over all alpha and all beta. I'm only summing over at the condition where alpha is less than beta. All right, so now note that we can write an antisymmetric tensor in two different ways. First of all, f is our antisymmetric tensor. Regardless of how we represent it, this is its let's say non-coordinate form. It's just the antisymmetric tensor f. And if we write it in this form here, we're going to call that the strict basis. The strict basis. And that means that, all of the components are these guys with alpha less than beta. So there's 6 components in the strict basis. However, this is a totally legitimate member of the 0,2 tensor product space, and we could write it in this basis as we did before. And the 0,1 component, F01, is equal to the opposite of the 1,0 component. And I've actually made that substitution here. But remember, the actual component here, so this tensor, let me erase this and give me some room. This tensor f is actually still f alpha beta e alpha tensor product e beta, with the stipulation that f alpha beta equals minus f beta alpha. Now I've made that stipulation explicit in red here. But the component here, this component, negative f01, that still equals f10, right? f10 is this object. And that's what this guy is saying. Now here you just have to know, you have to be told that this is an antisymmetric tensor. So you have to remember this fact. But in this basis over here, you don't have to remember it. And if you write it in the strict basis, you don't have to remember that at all. Okay. So with that in mind, what's our next step? Well, now we have to understand that if we're going to use a different basis, we have to understand the rules of things are different in different bases. So this is the standard rule for raising two indices, right? The standard rule is f with the contravariant, the contravariant indices, or the contravariant components of the tensor f, are equal to the covariant components of the tensor f multiplied and Einstein summed in exactly this way, where we use the metric to raise the indices. This is pretty standard stuff that's well known. In fact, I could just for illustration, I'll blow this up for the F2,3 case, meaning I'm going to choose mu equals 2 and nu equals 3. Okay, so that's the obvious expression of this for the specific 2,3 case, where mu and nu get substituted for 2 and 3, and then this gets blown up as an Einstein sum. And the first step of the expansion is I just expand the sum over alpha. So there's the 0,0 term of alpha, the 1,1 term of alpha, the 2,2 term of alpha, and the 3,3 term, and of course we're summing. So that's the Einstein sum for alpha. And now each of these we blow up with a beta. Okay, so this is the blown up part, right? So now I've taken these betas and I've expanded them and I get this thing. So all we have to do now is execute this sum to find the one component F2,3. So, this notation is very compact, right? I mean, it's obvious what you have to do, but it's always fun to kind of blow it up and actually see the mess that these raising and lowering indices is actually all about if you were to actually do it with a real metric and a real tensor here. Now, the fact that we know that we're dealing with an antisymmetric tensor means a couple things. First of all, it means these guys are 0, right? Because the diagonal elements of the f are all 0, meaning f alpha alpha equals 0. So those guys go away. And then we also know that f01 is equal to the opposite of f10. So we could make that substitution. Understand that when we make that substitution, we're stipulating that the component f01, or let's put it this way, let me undo that. The component f10, that is always the component that lands in front of the E1, E0 basis vector, no matter what. The name of that thing is always f10. It just so happens that we can replace f10 with minus f01 because we're dealing with an antisymmetric tensor. But it is correct to say that the f10 component of the tensor f cast in the basis E mu tensor product E nu, right? In that basis, this tensor cast in that basis has an F10 component, and that F10 component happens to be the opposite of F01. The reason that's important is because we kind of always refer back. Ultimately, all of our notation really does refer back to these component names, despite the fact that we change basis to this basis later, right? For example, here you can see it. F01 multiplied by just this term, that's clearly the F01 component we're talking about in in this basis, right? That's the same F01. So even though we're actually in this basis, F01 is the same component as in the other basis. There is no F10, however, in this basis at all, because as you see, the F10 would require E1 wedge E0, and first of all, that is contrary to our increasing indices thing, but more importantly, the reason we don't have that is because E1 wedge E0 just simply equals the opposite of E0 wedge E1, right? Obviously, if you switch these two around, you're just going to change the sign. And the point of that is that this guy is not linearly independent from that guy. So it's not really part of the basis, right? That's the story there. Anyway, to get back to this, I can make all of these changes. I can, everywhere I see a non-strict index, I just swap it out with the opposite of the strict version, right? So I'm going to put a -10 here, and I'm going to do that for every index. Okay, and that ends up looking like this. So every one of the non-strict orderings, I switched and I added the minus sign. And so then the next step would be I'm just trying to demonstrate that for antisymmetric tensors, if you actually now combine the F01 terms, you end up with G20, well, you end up with this. You end up with G20 times G31 minus G21 G30, right, times F01. So that's a result of combining this multiplied by this and this multiplied by this. So there's that negative sign that comes down here, and you end up with this expression in F01. And if I do this for all of them, I simply come up with there's only going to be 6 of these, right, because the diagonal ones are gone, and I've swapped out the non-strict ones with the strict ones, so there's only going to be 6 of these. So let's see what happens. So if I've done the calculation correctly, you end up with this expression here. There's 6. So now I have these 6 components, and I have this is what's left in order to calculate this one contravariant component, or this one contravariant component. So I now can look at this in a slightly different way, because I know that these are the components of the strict basis, right? I can write this as, remember, F alpha beta E alpha wedge E beta. And here are those strict components right here. So what I've effectively done is I found a way to raise I've found a way to raise strict indices. This is how you would raise a strict index. You would go in this case, the strict index I'm raising is the 2, 3, and I have all of these things. But this is not just simply the classic formula for raising and lowering indices. This is the regular formula for raising and lowering indices, where this are all of the components in the tensor product basis, right? This is the famous formula. Now this has told us, we've discovered sort of a new formula for raising strict indices. And I didn't finish this here, but a strict index, you can consider this, right? F alpha beta E alpha wedge E beta, right? You're switching from the second exterior power of p forms to the second exterior power of, often called, well, I guess we'll call them p vectors, right? So you can make that, but that's what raising and lowering these strict indices would represent. And they can be done, but you cannot use this formula to do it. What formula do you use? Well, this is very suggestive. If you look at these things, each of those looks like a little 2x2 determinant. And so sure, it's going to end up being the minor determinants of a 4x4 matrix. And this is that formula. It's something you probably haven't seen before, because I don't know if anybody actually goes through this. But to raise a strict index, which means we're raising a member of the 0-2 tensor product space expressed in the E alpha wedge E beta basis, to raise those components, so that would be F, whoops, I'm sorry, I want to raise E alpha wedge E, wait a minute, what do I want to do? Hold on. Yeah, so I want to, this guy, all right, sorry, this is confusing to me sometimes, of course. E alpha E beta, that is the basis for that of which these are the components in this basis. The reason I don't have these marked off as strict is because this summation is enforcing the strictness, right? But I could do it this way too. That would be redundant to have the strictness there, but that's fine. I'll just leave it so that the fact that alpha and beta is strict indices in this basis will be enforced by the sum, where alpha is less than beta. And then I have this interesting symbol here, which is it starts with mu nu and then a comma and then alpha beta, which is summed over F. So what is this symbol here? Well, that symbol is a determinant. It's the determinant that will lead to each of these terms, each of the terms that you see there, because each of these guys will be a determinant, a minor determinant. And the matrix from which it's a minor is the following matrix. So this matrix is the matrix that this is sort of our base matrix. And this represents one particular minor, right? And the minor is a determinant of a submatrix of this guy. And this will be a 2x2 minor. So, for example, here, 2031 minus 2130, 2031, this product, minus 2130. So this is the submatrix whose determinant is the relevant minor that is the factor of the 0-1 term. So this guy here would be, I would write this as F23 equals the sum of alpha less than beta of G23 comma alpha beta F alpha beta. And then if I take the 0-1 version of it, it's the 0-1 term of that sum, it's G23 comma 0-1 comma F01. This thing here it has got to represent the determinant of this little submatrix. So how do we interpret that? Well, I think the way you can do it is you can say, okay, this 2-3 means you eliminate the second and third column, and this 0-1 means you eliminate the 0 and 1 row. What's left over is the matrix, you take a determinant. And by the way, this is totally generalizable to any rank. Remember, we're dealing with a 0-2 rank antisymmetric tensor, and we're trying to raise it into a 2-0 antisymmetric tensor, right? But, you know, you could do this for a 0-7 rank antisymmetric tensor. This is still well defined. It would just be something like F, let's see if I can do this, F I1, I2, to I R would equal the sum of K1 less than K2, less than KR of G I1, IR, where this is the same sequence as this, comma K1, KR, and then it would be F K1, K1 dot 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 KR, right? So we're trying to find the I1, I2, I3, IR component, and we take the component we're seeking, we put it in the left side of the comma for this symbol, and then we sum over all the strict values of of R indices, which we sum over here. We put that on the right side, and this represents a minor. And this minor would just be, you would do the same thing. You would cross off the I1 row, the I2 row, the I3 row, all the way to the IR row, and you would cross off the K1 column, K2 column, KR column. Whatever's left over, you squeeze into a matrix, find the determinant of that thing. And that determinant could be a 3x3, a 4x4, could be harder than a 2x2, but you just have to open your math book and figure out how to do it. And then that becomes the part of the sum. So raising and lowering indices in the strict basis is much more of a chore than this, right? I was able to expand that out without any trouble. This one, you have to if you were actually going to put these terms in here, you have to think about it. You have to form determinants and all that. But that's all an artifact of the fact that we're using a basis in the second exterior power. So the point is, whenever you are operating in the point of this, that's a good point. What's the point of all this? When you're operating in the wedge basis for the exterior power for an antisymmetric tensor, it only works for antisymmetric tensors. You got to remember the basic rules that you're used to don't apply there, and that's not totally uncommon. This actually happens in elementary general relativity when you are introduced to tensors, that are introduced in the usual way, in the usual basis. When you're introduced to tensors, eventually you're introduced into something called a tensor density, right? A tensor density. And a tensor density also is given to you as something that has different density, right? And when you do a tensor density, you realize the way they define it is it transforms differently than a tensor. It has extra factors of the determinant involved, right? Well, that's all an artifact of this. It turns out tensor densities are simply regular tensors. It's totally normal tensors, but they're expressed in a different basis. And of course, you never see this in general relativity books because they don't talk about the basis of these tensors in normal GR books. But tensor densities are normal tensors. There's nothing different about a tensor density. It is always a tensor. It's in a tensor product space. It has a rank, but you're expressing it in a different basis, and therefore it has a different transformation rule. And the transformation rule for tensors really depends on what basis you're in, right? If you're in this regular tensor product basis, you have the standard transformation rule we've always learned. As soon as you go to this basis, however, not this basis, as soon as you go to the wedge basis or the strict basis, that's not the rule anymore. You can't transform the components the usual way. And if you want to dig into that deeper, go back to the What is a Tensor lecture. Okay, so we've basically reviewed this idea, and these are all called two forms. I'll remind everybody that anything expressed in this basis is also called a two-form. Actually, a two-form, let me be careful. A two-form is ultimately a second-rank antisymmetric tensor. It's a second-rank antisymmetric tensor. It's a zero, I should be very specific. It's a 0-2 antisymmetric tensor. So it's a 0-2 rank. Sometimes this is called the valence. It's a 0-2 rank antisymmetric tensor is a two form. And we have reviewed two forms. And everything I just did for two forms, you can do for three forms and four forms. What happens is these vectors here become more complex, or they become a completely antisymmetrized collection of three vectors. For example, if you did this exercise here, where you take of the fully antisymmetric tensor and you write it out in the tensor product basis, then for a three form, the basis vectors would be E alpha wedge, E beta wedge, E gamma, ultimately. And they would be formed of E alpha tensor product, E beta, tensor product E gamma. These guys, there would be a combination of these guys that would make those things. For example, you would have E0, tensor product E1, tensor product E2, plus, I think this would be it. This would be an example of a completely antisymmetric basis vector for the third exterior power, right? If you switched E0 and E1, then you would switch this with this, right? And you would switch that with that, and you would switch that with that. And every one of those things would just change sign, and you would change the sign of the whole thing. So the analysis works for any dimension, and that determinant thing likewise works for any dimension. Okay, so with that in mind, let's move on and get back to the Riemann tensor. All right, so let's remember about the Riemann tensor. We started with the Riemann tensor because we have a metric in our system. And remember, we don't need the metric to define the Riemann tensor. We just need the connection. But anyway, once we have a metric, then we have this guy. And we know that this guy is antisymmetric in the first two indices, which we reflect by saying it's equal to its sort of antisymmetric part here and here. Now, if we were to look at these components and we write them down in our system of obsessively taking around the basis vectors, we would write it like this. dx beta tensor product. I don't like my tensor products. Right, this is the full expression of the Riemann tensor, the fully covariant component. They would call this the fully covariant form of the Riemann tensor, but it's really the fully covariant form of the Riemann tensor components. And then this is the basis for the 0, 4 tensor product space. That's what this is. This is the basis of that. And what we know, because we know this from the work done previously, we know, for example, that this is going to equal minus, we know that R alpha beta gamma delta equals minus R beta alpha gamma delta, and it also equals R beta alpha delta gamma, where I switch these two and these two, so the two negative signs cancel. But I know about that form of symmetry. So what I can actually do is I can actually take this and I can write them in strict components, and I could say that this same tensor also equals, I've got too many equal signs here, it also equals this. So in our method where we keep the basis vectors, if we want to think of this in terms of strict components, it's really not that hard, because we have a 2 form which matches the strict component of the first part here, tensor product with a 2 form with the second 2 components. And this is a completely legitimate object that is a 0,4 tensor, but it has the symmetry of the Riemann of this fully lowered form of the Riemann tensor, in that if you switch alpha and beta, you introduce a minus sign, and if you switch gamma and delta, you introduce a minus sign. So you can think of it completely in this way. And if you choose to think of it in this way, then, well, first of all, if you ever wanted to raise or lower the indices, the strict indices, you would have to start using the rules we talked about, and you have to apply them quite carefully. But once you think about it this way, you can now apply what we learned in the What is a Tensor series about the Hodge dual. And you remember that you can take the dual of any p-form, and the dual of a p-form is another form that is in the complementary exterior power space. Now, I'm not going to go over this in profound detail, but we do know that the 1 form, or the 0 forms, are functions, and that let's see, I don't need to do that. 1 forms, right, their basis vector would be dx alpha, or is not one, why don't I have a 1 form there? 1 forms have a basis vector of dx alpha, two forms are dx alpha wedge dx beta. Three forms, dx alpha wedge dx beta wedge dx gamma. And then you could have a four form, which would be dx alpha wedge dx beta wedge dx gamma wedge dx delta. Now, if you're dealing, and then remember, so this is designed to have you remember what we talked about in the What is a Tensor lecture. But if the underlying vector space is four-dimensional, if it's four-dimensional, then this last one here, then if it's four-dimensional, then we try to do the fifth exterior power, you would end up with a wedge dx epsilon, right? But now, if you tried to do this, you would duplicate one of these one forms. If you said alpha was 1, beta was 2, gamma was 3, delta was 4, epsilon would have to be 1, 2, 3, or 4. And we know that when you duplicate one of the one forms in this sequence, it'll all go to 0, right? You can't anti-symmetrize that way. So four forms are the limit for four-dimensional spaces. So there is no fifth-dimensional space. So that's one quick thing to remember. If this is unfamiliar to you, just go back to that stuff. I'm just trying to sort of review it a little bit right now. And but the other part I want to review, the key part, is that there's this process called the Hodge dual, where I can go from the first exterior power, and I can create a map to the third exterior power. From the 0th exterior power, I can create a map to the fourth exterior power. The dimension of this power, the dimension of the 0th exterior power is 1. The dimension of this exterior power is also 1. There's only dx0, dx1, dx2, and dx3. That's the only possible wedge combination you can have. Any variant of that by shuffling the order just changes it by a sign, which is really not a linearly independent basis vector. So this also has dimension 1. Dimension equals 1. So these two spaces are actually, you can map them together. Likewise, you can map these two spaces together. And the second exterior power you can map into itself. And that's process what we call the Hodge dual. The Hodge dual. And I'm not going to go into how to actually calculate the Hodge dual. It's a bit of an intricate process to prove, but once you've proved it, it's pretty easy to see how it's done. The point is that once we have the Hodge dual and we understand how it works for two forms, when I go back to this structure here, I realize what I've got is a two form and a two form. And I can consider the object that is the Hodge dual of this two form part and this two form part. And it's directly related to this object, right? It's directly related to this object. So we can now consider how would we write it? We would write it, let me see how we would write it. We would write it something like this. First of all, because everything is linear, let me put this to a new screen. All right, so let's say I call this thing equal to R, right? This is R. I want to know what the Hodge dual is. So I'm looking for R Hodge dual. Well, I can't, right? I'm not allowed to ask for the Hodge dual of R because the Hodge dual only makes sense if we're dealing with a P form. This object is not a P form. It is the tensor product of two forms, right? So asking for the Hodge dual of R makes no sense. However, what I can do is I can take the Hodge dual of this guy, because that's a two form, and the Hodge dual of that guy. And because everything is linear and the process of taking the Hodge dual is linear, this coefficient actually remains the same. So what I'm kind of looking for is an object that looks like this. R, alpha, beta, gamma, delta, times the Hodge dual, which is usually a star put on the left, of dx alpha wedge dx beta, tensor product, Hodge dual of dx gamma wedge dx delta. Right, something like that. And we actually calculated the Hodge duals of all the basis vectors for two forms. So I calculated the Hodge dual of dx0 wedge dx1. I calculated the Hodge dual of dx0 dx2, dx0 wedge dx3, dx1 wedge dx2, dx1 wedge dx3, etc. All of these have Hodge duals, and the Hodge dual is always going to end up being the strict form that's missing, the two missing ones. So it'll be dx1 wedge dx2, and the question is it plus or minus, right? And we worked it all out for this case and got all those answers. And if I literally just substituted those answers in here, I would find what we are going to call the double dual, alpha, beta, gamma, delta. This is the double dual in terms of the language of Meissner, Thorne, and Wheeler. So Meissner, Thorne, and Wheeler doesn't really do this. They don't actually break it up the way I did, but I want you to see that because the way Meissner, Thorne, and Wheeler does it is he just says, okay, we've got R, alpha, beta, gamma, delta. That is the completely covariant Riemann tensor. And what we're going to do is we are going to turn it into, we are going to take its double dual. So this guy is just a regular tensor in the regular old tensor product basis, d alpha tensor product, dx beta tensor product, etc., right? It's essentially, what is it? It is this thing right here, right? It's that thing right there. We're going to take that thing, and all of the symmetry is buried in the components right now. Right here, the symmetry is buried in the basis vectors, but here the symmetry is buried in the components. When you bury the symmetry in the components, you can still take the dual of it in that component basis, and in fact, it's not that hard. And what he wants to create is this guy, G alpha, beta, gamma, delta, little line through it, and it's going to equal this thing. And this thing here, that's the process. That's the process of taking the dual of this and this, but in the other basis, in the regular tensor product basis, dx alpha, in this basis here. Now, notice one of the first steps we do is we raise these two indices. So we actually take R alpha, beta, gamma, delta, and we move it to R mu, well, R, I guess would be alpha, beta, rho, sigma. We raise two of the indices. So when we do that, we immediately drop these two guys, and in the coordinates basis, this would now be partial, well, let's see, this guy here would be, let me just get it right. Yeah, how big of me? I want to get it right. So this is the basis for this guy. This guy is actually in a very, it's actually, you can't write the rank of this guy down the way Meissner, Thorne, and Wheeler chooses to raise and lower the indices. It's a perfectly fine tensor, but it's just backwards, right? You can't call it a 2 rank tensor because this always implies the sequence would be covectors before vectors, right? So here we have vectors before covectors. So you would normally have these. In other words, you would normally have the vectors on the front end of a tensor and the covectors on the back end of the tensor in what we really want to call a tensor. So this is kind of a little bit backwards. This is one of those places where you actually sort of ignore that convention. But the point is once you build that thing, which is just raising and lowering using the regular rules, right? Because we're using the regular tensor product basis, use the regular rules, and then these Levi-Civita symbols then do all the magic that turns it into its so-called double dual. Now, remember, we talked about the double dual in what is a tensor, but there we talked about the dual of the dual space, and we called that the double dual. And that's not what this is. This is called the double dual because you actually have two p-forms living in here, right? Two p-forms, and each one can be taken a dual of. You could do a single dual if you wanted to. It's just not particularly useful, but it is what it is. But here you do this double dual. There's another notation for it. This form, and this is just taking advantage of how to define a generalized delta function. This is called a generalized delta function, and that's really this combination of Levi-Civita symbols. These two, essentially, it's a sign change, right? All of these have to equal all of these in the sense that this has to be the same sequence this here has to be a permutation of this. As these indices have to be a permutation of those indices, and if it's even or odd, you get a plus or minus 1. And there's a double counting problem if you'd use this, so you end up with another factor of 2 down there. But ultimately, notice that the final result is, in fact, in regular tensor form with the contravariant indices first and the covariant indices second. So that's the problem with this one. The contravariant indices are first. The covariant indices are first and the contravariant indices are second, which is a little non-standard, right? It's certainly fine, right? Because you can raising and lowering doesn't really care. It's just you lose the ability to define the rank very unambiguously, right? Because this rank always counts. These are the contravariant and the covariant components is the way this rank is defined. So it's just a technical matter. I brought it up in the What is a Tensor series, saying these are tensors and these other things, they're not tensors. And it caused a lot of confusion. I kind of wish I never mentioned it, but it is correct. It is true. In order to have this rank, you have to have the right sequence of things. And the first one represents components that are contravariant, and the second one represents components that are covariant. Anyway, so that is the double dual of the Riemann tensor. Notice we've added nothing. The Riemann tensor, if we started from our derivation, which was R, alpha, beta, gamma, delta, like that, that immediately can be converted into this form with the presence of a metric. That's why it's metric induced, right? We can immediately get that, and that adds or changes nothing. It just moves it from one tensor product space to another. This guy is nothing more than a mathematical way of combining these components. That's a constant. So this thing doesn't have any fundamentally different material about space. It's literally just another form of the curvature tensor. So that's why it is a metrically induced property, because only the metric matters, because that's the only way to raise and lower the indices. But we will see later that this guy's kind of convenient and cool to help us understand certain things like the Bianchi identity and the contracted Bianchi identity. I'm not sure if it really adds a lot of enlightenment, but it did give us the opportunity to quickly review p-forms in a very rudimentary way. In What is a Tensor, we went through this in much deeper detail and did many, many lectures on it. But so this is a very rudimentary way. And I think it's fun to see how the Riemann tensor in its fully covariant form actually can be thought of as the tensor product of two forms, the tensor product of two forms, which immediately allows you to think about taking the Hodge dual of each of the two forms, which immediately gives you this thing which we call the double dual. And normally you don't see this in general relativity courses, and I'm not sure it was it in itself is worth the time. I'm not sure that this is such an important thing to know about. It certainly isn't as important as the Weil tensor, alpha, beta, gamma, delta, and it's certainly not as important as the Ricci tensor or even the scalar curvature. But it is among them. It does sit in that class, and I wanted to point out its existence. Okay, so the next lecture we will introduce these guys, and then we will have all four of our metric-induced Riemann tensors.